Stan here, continuing the saga of logarithms in a nutshell. So far we've been dealing with base 10 logarithms, but there's another kind of logarithm, and that uses a base which is an irrational number called e, the exponential constant. It's actually an irrational number equal to approximately 2.71828. If you want to look at it in a little more detail, and you have a Windows 7 computer, it has a calculator. Windows 7 has a scientific calculator mode. Enter 1, then hit the INV key, which means inverse, and then hit the LN key, which means natural logarithm. That LN should then change to an e to the x. You're going to get e to the first power when you do that, and of course anything to the first power is itself. And then you're going to get 2.71828 and a whole bunch more digits. Well, this irrational number e, why on earth would anybody pick an irrational number like this? It just seems totally obscure. Why would anybody pick that and consider it special for any reason over any other number, like 2 or 10 or the square root of 2 or pi or anything else? Why would they pick this? Well, as things work out, this number has a variety of interesting properties. One of the most interesting is that it is the sum of an infinite series. If you take 1 plus 1 over 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus ... and you add up this infinite series. In the wonderful world of mathematics, you can do that. You will get e. If you just run this out to a whole bunch of terms, you will find that you get a sequence of partial sums of this infinite series which converges on the value of e. Remember what factorial means. N factorial, where n is any positive integer like 1, 2, 3, 4, equals 1 times 2 times 3 times ... all the way up to n. So, for example, 7 factorial would be 1 times 2 times 3 times 4 times 5 times 6 times 7. So that's one of the interesting properties of e. Here's another one that was discovered by a mathematician long ago. You know how compound interest works. You get a bank account these days with an interest rate of something like 0.00000000000001%, while inflation runs at something like 15% per year. The rich get richer, the poor get poorer. You save your money. And I'm being a little facetious, but it's not much different than that. I believe that this is the rate I'm getting. my savings account right now. Well, you save money. Yeah, right. You save money, you lose money. It'd almost be better burying your currency in your backyard. Just make sure your dog doesn't dig it up and eat it. Anyway, the thing, not that it'd be worth much less at the rate we're going, but now I'm getting off. The point of the matter, though, in this context, suppose that you were lucky enough to find a 100% per year annual percentage rate APR certificate of deposit. 100% per year. That means that if you put in $1,000 on January 1st, that on December 31st of that year, you'd have $2,000. 100% per year. Now suppose that the interest is compounded more and more and more frequently. You get a little better deal if it's compounded quarterly. You get a little better deal yet if it's compounded monthly. Even a little better deal yet if it's compounded daily. Now suppose that you just kept compounding it more and more and more often until it was being compounded continuously. 100% interest rate, and that is compounded continuously. Now suppose that on January 1st, you put in X dollars. Then on December 31st, you're going to have X times E dollars. In other words, if you start out with something like, say, $1,000 on January 1st, then on December 31st, you're going to get 1,000 times E, which would be 2,718, roughly $2,718.28. That is assuming a 100% interest rate. That means if it was only paid once a year, you'd get double your money. But if you compound it more and more and more often, you're going to approach this figure, and if you could somehow compound it continuously, not even every minute, not even every second, not even every nanosecond, continuously, you'd get that. Well, those are just two different ways of defining this exponential constant. Exponential constant, which is also known as the natural logarithm base, and that number is called E, and it's roughly equal to 2.71828. Now that we know all that, and we've got this number E firmly in our minds, we can progress to the next level of the logarithms in a nutshell saga and start to work with natural logarithms. Until then, Stan Jabalisco saying so long.